Greetings, everybody. In this video, we're going to talk about finding power series solutions to differential equations near a regular singular point. Okay, so I'm going to start this with an example, and then we'll talk about what all those words mean, and then we'll talk about what to do about it. Okay, so here's the differential equation I want to look at. Very simple. We're going to look at this guy. Just a first order differential equation, just to get a hang of the idea of what's going on here. All right, you could probably solve this using techniques that we've talked about in previous videos very early when we started talking about things. This is not a hard differential equation to solve. We're going to look at it from the standpoint of power series solutions so that we can discuss how to carry those techniques and deal with the issue that this differential equation presents in a more general setting, right? So when we look at power series solutions, we're going to try to find a solution of this form. All right? And that just means that y is some infinitely long polynomial, right? And it's up to us to find the values of these coefficients that make this power series work in this differential equation. Well, what we were doing before is we were saying, well, we're going to just plug this stuff in there. Well, to plug this in, I need to compute y prime, right? So I compute y prime. Let me leave that index off for just a moment. When I take the derivative of that, I bring the n down and subtract 1 from the exponent, right? That's how we take derivatives. Now, when you think about it, what happens is the first term here was a constant term, the n equals 0 term. The derivative of it is 0. So it doesn't appear here. So we don't have an n equals 0 term over here. So we start this at n equal 1. And just to expand that out, what we would be seeing here is, if we were to write this out, starting with n equal 1, I have a1 times 1, x to the 0, plus 2a2, x to the 1, plus 3a3, x squared, etc. And the series goes on, right? Now, if I were to start this at x equals 0, we see we'd have a problem, right? Because then I'd have x to the negative 1. But I can see that when I differentiate these, I don't get an x to the negative 1. That would be wrong. So do be careful about that. Now, when I plug this in, I want to compute xy prime, right? So I can just stick it in there. So let's see what happens if I compute xy prime. Well, I'm going to multiply everything by x, right? So all I'm going to increase the exponent by 1, so this will become x to the n. Or in other words, if I multiply everything by x, I get this, etc. All right, so now I'm going to plug this stuff in. So I'm going to be taking this term and adding this guy, right? So I'm going to be taking these and adding these, okay? And what I'm going to get an infinitely long polynomial when I add those together. But because the right-hand side is 0, that's telling me that the coefficients of that polynomial must all be equal to 0. Okay, 0 is a polynomial. You can think of it as a polynomial all of whose coefficients are 0. And when two polynomials are equal, their coefficients match. So I'm just going to match these coefficients to that. Now, when I add these, I start with the n equals 0 term, right? That term appears in this series, but it doesn't appear in this one. Okay, so it's all alone over here. You can see what it is. So that has to be equal to 0. Okay, so the n equals 0 term, and we start with n equals 0. This doesn't have a contribution, but this one does. It's just a0. Okay, and it has to equal 0. So that's my first equation. When n is greater than or equal to 1, I have contributions from both of these series, right? So I know that n times an plus an, I'm just doing this, it has to equal 0. Okay. Well, let's look at this equation here. I can factor out an an. Okay. Now, n is greater than or equal to 1. This isn't 0, so I can divide both sides by this quantity, right? So I can just kill that. I see that an equals 0. So what I'm getting is that a0 is 0 and every other an is 0, so all the ans are 0 from 0 on up. So what this is suggesting is that it's saying that every single one of these coefficients is 0, so my entire polynomial is 0. It's suggesting that my solution is simply y equals 0. That's all it's giving me. Now, is that a solution? Well, yeah, it is a solution. You can check it out. It does work. Is that the only solution? Well, it turns out it's not. So somehow we've missed some solutions. What went wrong here? Well, this is what it means to have an ordinary point. If you have this x here, and we try to make a Taylor series centered at x, centered at 0, or we call that a Maclaurin series. That's what this is. It's a Taylor series centered at x equals 0. In other words, a Maclaurin series. And this has a factor of x minus 0, some piece whose root is 0. This is called an ordinary singular point. And this is going to cause problems like we're seeing here. I didn't get a complete solution. I got a solution, but it's not the full picture. So what is the trick here? Well, if you do investigate what the solution is, you'll see that we should probably try something like y equals x to the r, right, for some non-zero r. And we might find that there's an an exponent that we didn't consider in these power series that might work. Okay? So if I try that and I compute y prime, what do I get? I get this. And if I look at xy prime, I get this. If I plug these into the differential equation, let's see what I get. The differential equation said this plus this. So I'm going to have this guy plus this equals 0. That's just xy prime plus y equals 0. Well, I can factor out the x to the r. And I can see that the only way this function can equal this for all x is if r is equal to -1. Right? At least for all x for which that'll be defined. And so I see from this, what I'm really doing is I'm solving this polynomial equation here, and I'm deducing that r has to be -1, which is telling us something. It's telling us that a solution to this differential equation is x to the -1. So yes, y equals 0 is a solution, but so is this. In fact, you might also, if you do a little bit more investigation, you'll realize I could have put any constant here, and that would have worked. I would have just had a constant carried out throughout this whole thing, right? So any constant times x to the -1 works, and in fact, when I let that constant be 0, that's giving me my solution y equals 0. So this is the general solution to that differential equation. So this is something we need to be careful about. We need to be careful about if I try to expand a series about 0, and 0 is a root of this leading coefficient, that's cause for concern. And that's called an ordinary singular point. Let me show you a more detailed description of what's going on here. Here we have a theorem. Well, this is just a definition of what an ordinary singular point is. It says, let P0, P1, and P2 be polynomials with no common factor. And if there was a common factor, we could factor it out, right? Suppose that P of 0 of x0, this is where we're going to center our series about. I was centering my series about 0, and that's what made it a Maclaurin series. Then that point, that number that we're centering it about, is a regular singular point if this thing can be written in this form. Right? And that's actually what we had. Now we're having it as a first order differential equation, right? So you can ignore that second order stuff, but it's the same idea. And that's exactly what we had. My x0 was 0, so you don't see that piece. I'll just kind of cover it up with my pen here. And we could have written the differential equation like this, where b and c are polynomials. And that's exactly what we had. Okay. Our polynomials are very simple. They were just, if I wanted this to look like this, I would just take x0 to be 0, right? B to be 1, and c to be 1. And it certainly does look like this. And that makes 0 a regular singular point. Okay. So when we have a regular singular point, what we're going to do is exactly something like what we did. We're going to try solutions like this and look for solutions that might have exponents that aren't positive integers. Okay. Now let's go to a more general setting. Let's go to the second order setting. Okay. This is called an Euler equation, named after Leonhard Euler. Notice that the powers on the x match the order of the derivative that we see in each case. X to the 1, 1 derivative. X to the 2, 2 derivatives. Right? X to the 0, 0 derivatives. So that's an Euler equation. Now, this has a regular singular point at 0. Right? 0 is a regular singular point because this is a second order polynomial of degree 2 with 0 as a root. This has 0 as a root, just like they were describing here. It's x minus 0 squared times some polynomial, x minus 0 squared times some polynomial, etc. In this case, our polynomials are just constants. Okay, so what do we try? Well, like we did before, we try y equals x to the r, where r may not be a positive integer. Well, let's see what happens here. Then y prime is equal to, and y double prime is equal to, okay, plug this stuff in there. What do we get? Well, plugging this in for y double prime, and notice the x squared is going to multiply by this, and it's going to kill the minus 2, right? The x here is going to multiply by this, and it's going to kill the minus 1. And then I'm just going to take this times this. So just plugging that in, I see that this has to be true. Well, I could factor out the x to the r, right? Which means if this is going to be true for all x, this thing has to be 0, right? This is called my indicial equation. And solving this for r is going to give me my solutions. Okay. So there are 3 situations. This is a second order polynomial, second degree, right? So it will have 2 solutions. Now it might be a single solution that's repeated, right? But we know that you could have, there's 3 cases, right? You could have 2 distinct real roots. You could have 1 repeated root, 1 real repeated root. Or you can have, the third possibility is you could have 2 complex solutions. These are the 3 possibilities for a second degree polynomial. Well, what do we do in these situations? Well, there's a theorem that we have that describes exactly what we're going to do. Okay, so let's go take a look at that. So it says, suppose the roots of the initial equation are R1 and R2. Okay. Then a general solution of the Euler equation is going to be given by one of these three forms. It's either going to be a linear combination of x to the powers corresponding to the two roots, or it's going to be x to the repeated root power times this term, c1 plus c2 log x. That's what happens if the two roots are the same. We have a repeated real root. Or it's going to be of this form, where if we have two complex roots. Remember, complex roots always occur in conjugate pairs. So one's going to be of the form lambda plus I omega, and the other one's going to be in the form lambda minus I omega. So they both can be written like this, right? In which case our solution looks like this. Now this should look familiar to you, right? This is similar to what happened when we were looking at the characteristic equation corresponding to second order differential equations, right? Very similar setup, very similar sequence of things occurred. So this is what we're going to be looking for, okay? So let's do an example of a problem where something like this will happen. Okay, so here's our example. Notice that this is an Euler equation, okay? So that means what we're going to do is we're going to look at our indicial equation that comes from this, right? Which, if you recall, was r times r minus 1 plus 7 times r plus 8 equals 0. Okay, so let's find the solution to this. Let's see what happens. Looks like I get r squared plus 6r plus 8 equals 0. Let's see. I think that's factorable. That's pretty nice for us. This is r plus 2 times r plus 4 equals 0. So I see I have two real roots, right? R equals -2 and -4. So in the case of two real roots, what do we do? Oops. Where did that go? Where did our theorem go? Here we go. In the case of two real roots, we are going to use this formulation for the solution. C1 times x to the r1 plus C2 x to the r2, a linear combination of those two terms, right? So our solution is C1 x to the -2 plus C2 x to the -4. There we have it. And go ahead and check this out to verify that it does indeed work. Okay, let's go to our next example. Okay, here's our next example. Again, it's an Euler equation. So let's check it out. The indicial equation is going to be as follows. Let's multiply it out, see what we get. Okay, so let's see, I don't see a nice way to factor it, so let's go ahead and use the quadratic formula here. Oh, it's stupid. I should have seen the factorization. I didn't see that. So actually, yes, we get a repeated root. There was an obvious factorization, right? R minus 1 squared equals 0. For some reason, I was expecting a different kind of solution here. Okay, but yeah, so so what does this mean? That's embarrassing. Forget we didn't do that. We could have factored it, right? There's a repeated root, right? R equals 1 is a repeated root. That's how many times it's repeated? Twice, right? So in that case, what do we do? Well, okay, here we are. And in the case of a repeated root, we use this formulation, right? So that's what we're going to do. x to the 1 times c1 plus c2 log x is our solution. Okay? Okay, let's do that last kind of problem. Okay, so this is our third example here. It is an Euler equation. All right, so let's write down the initial equation. Oop, there's a coefficient 2 over here. Let's multiply it out. Okay, now this one, don't think this one is easy to factor. We're going to use the quadratic formula here. Okay, so let's see what we get when we simplify this thing out. Okay, so we got two complex roots here. Okay, so what do we do in this case? We go to our theorem and we see what we should do. So if the roots have this form, we're going to write our solution in this form. Okay, notice the real part of the complex root, it becomes the exponent. The imaginary part of the complex root gets multiplied by log x inside cosine and sine. Okay, so my solution and there we have it, our solution to the differential equation. Okay, so that's it. Just looking at some Euler equations, what we do in this case. So I'll catch you in the next video.